All right, when titrating with a weak acid and a strong base, it's a little more complicated than a strong acid, strong base titration because the conjugate of the weak acid plays a role in affecting the pH. So when we look at the titration of a weak acid with a strong base, there's 4 points of interest. A, before we add any sodium hydroxide, what's the pH when I just have the acetic acid? B, after I've added sodium hydroxide. C, at the equivalence point. And D, past the equivalence point. So when we do this, right, we're going to have when we add the hydroxide, we're going to have a neutralization reaction, right, and it goes all the way forward. So you add something to the beaker, right, the 25 milliliters of acetic acid, and something happens, and then you look to see what's affecting the pH. So the problems go like this. Or just reminding ourselves the sodium ion plays no role here, right? It's about the acetic acid and the acetate. All right, so before I begin this titration, what's in the solution at this point that's affecting the pH is the zero point 0.1 molar acetic acid. So in order to figure out what the pH is, this is a Ka problem. I'm going to lose X amount of the acetic acid, make X amount of acetate, and X amount of H+. Concentration of H+ will determine the pH of the solution. So solve for X. Again, I can ignore the initial change in the initial concentration because the Ka is so small and the initial concentration is large. So 0.1 multiplied by both sides, take the square root of both sides, and I get X. X is equal to the H+ concentration. Take the negative log and get the pH. All right, so to begin this titration, you're starting at a pH of 2.87. All right, so that's could be lower, right? This is a weak acid, so it's incomplete ionization. So we start at a pH of 2.87. All right, part B, or step B. I'm going to add 10 milliliters of the sodium hydroxide to the 25 milliliters of acetic acid, and I'm going to get a neutralization reaction. So what I need to know is what's in excess here, right? How many millimoles of the acetic acid do I have? How many millimoles of the sodium hydroxide? So if I have 10 milliliters of 0.1 molar sodium hydroxide, I've got 1 millimole of hydroxide, and 25 milliliters of 0.1 molar acetic acid is 2.5 millimoles of acetic acid. So ready, set, go. The reaction happens. The limiting reactant gets totally burned up, the hydroxide, and what am I left with in the solution that's affecting the pH? Well, in this situation, the acetic acid was in excess, right? So I didn't burn it all up. And while I was burning the acetic acid up, I was producing its conjugate base. So this is a common ion situation. I've got a high concentration of acetic acid and its conjugate base. So you could use the Hasselbalch equation to figure out what the pH is at this point. That's the easiest. So look at the Ka expression for acetic acid. All right, I've got acid and its conjugate base. So you can plug directly into the Hasselbalch equation, millimoles of acetate divided by millimoles of acetic acid, and the Ka value, and solve for the pH. Okay, so that's point B. Point C is the equivalence point. I'm adding 25 milliliters of the 0.1 molar hydroxide, so I've got 2.5 millimoles of hydroxide, 2.5 millimoles of the acetic acid. Ready, set, go. They burn each other up. And I ask myself the question, what's still in the solution that's affecting the pH? Well, that 2.5 millimoles of acetic acid went to form 2.5 millimoles of acetate. So that's what's affecting the pH at this point. This is a Kb problem. I've got acetate floating around in water. No more hydroxide, no more acetic acid, just acetate. So what I need to know is what the concentration of the acetate is, right? So you added 25 milliliters and 25 milliliters. So that's 50 milliliters of solution divided by millimoles of acetate gives me the molarity of the acetate. It's a KB problem, so I'm going to lose X amount of acetate, make X amount of acetic acid, and X amount of hydroxide. So plug those equilibrium concentrations into the law of mass action. Again, water is excluded. And I solve for it. Solve for X. X is equal to the hydroxide concentration. Take the negative log and get the pOH. Subtract from 14 and get the pH. So with a strong base being titrated into a weak acid, at the equivalence point, you've got a pH above 7, right? That's because you've got conjugate base floating around, right? This is a basic solution. All right, so that's point C. Point D, we go past the equivalence point. All right, so in this case, 35 milliliters of 0.1 molar sodium hydroxide is 3.5 millimoles of the hydroxide. That's going to completely burn up the acetic acid, and I ask myself the question, what's left in the solution that's affecting the pH? Well, you might be tempted to look at the acetate again, but no, the big one is the leftover hydroxide. All right, so that's the main thing. The contribution of the acetate here is going to be infinitesimally small with this common ion with hydroxide. So we just look at the hydroxide. So it's millimoles of hydroxide left over divided by the total volume. So 25 plus 35 is 60. That's the molarity of the hydroxide. Take the negative log, get the pOH, subtract from 14 and get the pH at this point. So there's our 4 points during the titration. The initial pH before I add anything, the pH before the equivalence point, the pH at the equivalence point, and the pH past the equivalence point. So when I do a graph of this, right, I do a pH versus titrant added graph, titration curve, I end up with a non-symmetrical curve. I end up with a flat curve, a flat spot in the curve starting out. That's the buffer. All right, so I'm adding my milliliters of hydroxide, but the pH isn't going up all that much because I've got acetic acid in there to burn it up. So the midpoint of that flat spot is going to be the maximum buffer, right, where I have the same concentration of conjugate base as weak acid, and the pH is equal to the pKa. I keep adding past that, and then boom, the big jump up, right? I've burned up all my acetic acid, and I get a pH at the equivalence point above 7 because of the conjugate base. And then I end up with excess hydroxide. So it's flat, jump up, and then it tapers off. All right, so this is you've got to be able to recognize what the curve looks like for a strong base titrated into a weak acid. Maximum buffer. All right, titrations involving strong acids and a weak base. Again, the conjugate of a weak base is going to be significant acid, right? So it's going to affect the pH. So it's a little more complicated than a strong acid, strong base titration. So again, 4 points of interest. The pH before I begin, pH after I begin titrating, pH at the equivalence point, and the pH past the equivalence point. Now this is going to be different. It's going to follow a different pattern because I've got a strong acid being titrated with a weak base. So I've got 25 milliliters of 0.1 molar hydrochloric acid in the cup, and I'm adding ammonia. So it's a neutralization reaction. It goes all the way forward. So again, you neutralize it, and you ask yourself what's left in the solution that's affecting the pH. So let's look at the first point before I add anything. All right, so what's in the solution affecting the pH? The hydrochloric acid, right? So I've got 0.1 molar hydrochloric acid. It completely ionizes to form 0.1 molar H plus ion. So take the negative log of 0.1 and I get a pH of 1. So this is what I'm starting out at. pH all the way down at 1, strong acid. All right, second point. I add 10 milliliters of the base. So I'll have 2.5 millimoles of the hydrochloric acid, 1 millimole of the ammonia, ready, set, go. The ammonia is completely burned up. I've lowered the hydrochloric acid concentration down to 1.5 millimoles and raised the ammonium ion concentration up to 1 millimole. So what's in the solution that's mainly affecting the pH at this point is just the leftover hydrochloric acid, right? So I've got 1.5 millimoles left over. I added 10 milliliters to 25. So I've got 35 milliliters of solution. Divide the leftover hydrochloric acid by the volume to get the concentration of the H+. Take the negative log and get the pH after I've added ammonia before the equivalence point. All right, going to point C. I add 25 milliliters of the ammonia, right? So I'm going to have a complete neutralization of the hydrochloric acid. So 2.5 millimoles burns up 2.5 millimoles, and what's in the solution affecting the pH? The conjugate acid of ammonia, ammonium ion. So at this point, it's a Ka problem. You've got ammonium ion sitting around in there. I want to know what the concentration of the ammonium ion is. So 2.5 millimoles divided by the 50 milliliters of solution I have. I'm going to get the concentration of the ammonium ion. I need the Ka value for ammonium ion to figure out how much it ionizes to form H+. So I'm going to lose X amount of ammonium ion, make X amount of ammonia, X amount of H+. Solve for X, right? Concentration doesn't change. All that initial concentration doesn't change. Multiply both sides. Take the square root of both sides. Get X. Take the negative log and get the pH. All right, so the pH at the equivalence point of a strong acid being titrated with a weak base is in the basic range. Oh, I'm sorry, in the acidic range because of the conjugate acid, right? The ammonium ion. All right, so in the acidic range. All right, and D, the last one. I go past the equivalence point. So I add 35 milliliters of the 0.1 molar ammonia. I burn up all the hydrochloric acid in there. I've got leftover ammonia. And for every 2.5 millimoles of hydrochloric acid burned up, I'm making 2.5 millimoles of ammonium ion. So I've got a buffer at this point. I've got ammonia and its conjugate acid. So I would suggest solving this using the Ka for ammonium ion just to be have a procedure. So both of these things are in solution. It's a common ion problem. I'd use the Ka for ammonium ion to solve for this. Plug these millimoles directly into the Hasselbalch equation, right? Conjugate base over the acid, and solve for the pH. And that's how you do these titrations. When I plot the data points, right? Initial pH, pH before the equivalence point, pH at the equivalence point, pH past the equivalence point. Again, it's not a symmetrical titration curve. It starts out by eating up all that hydrochloric acid, and then boom, you get the jump up, all right? And it's in the acidic range because of the conjugate acid of ammonia. And then it tapers out on the other side. It flattens out on the other side. That's where you've got the buffer. So the equivalence point is in the acidic range. And if I'm looking at the midpoint of that flat spot, it should be more towards the midpoint, it's going to be pH of 9.25, where I've got the maximum buffer. Same concentration of ammonia as ammonium ion. So you got to know what these curves look like. This one starts out curvy and then flattens it, and you have the jump up and then it flattens out, whereas the other one starts flat, get the jump up, and then curves off.